Welcome again. Our next speaker is Enrico Wegner from Maastricht, and he'll be talking to us about transmission channel analysis in dynamic models. Enrico, the floor is yours.
Yeah, thank you very much. So thanks for inviting me. This is joint work of all three of my supervisors, so Leonard Lieb, Stefan Smeekes, and Ines Wilms. And I'm indeed going to talk about transmission channels, but that's a very broad kind of used topic in macro. So let me maybe immediately come to like what motivated it. What do we mean with a transmission channel? So a lot of work in macroeconomics kind of focus on these impulse response functions. So usually what we do is we look at or we trace out the effect of a structure shock over time over various horizons and essentially check what that actually looks like. For example, what we might be doing is we have a contractionary monetary policy shock, which we identified and trace out direction of inflation. And what we usually observe is a decrease in inflation. What these impulse response functions, however, do not tell us is what the mechanism behind that is. So how a contractionary monetary policy shock actually decreases inflation. And that's the kind of the topic that we were interested in. So what are the mechanisms behind shocks? And that's also what we call a transmission channel. So transmission channel is just one specific mechanism behind a shock. What we then do in this paper and what I'm going to do here throughout the presentation, although much more in like intuitive sense in the presentation, is that we introduce a methodology that allows for answering these kind of how questions at the moment in like S-Varma models, so also a lot of linear SDSG models. We kind of currently extend it to general linear state-space models actually. If you're more related to like microeconometric literature, you might call this actually mediation kind of analysis, with the additional complication that we're in a dynamic setting and that we're in a general equilibrium setting where everything kind of causes everything else at the same time. So to understand the methodology, I'm actually going to use a very simple and here static macroeconomic model. So on the left-hand side, I essentially have my equations. I have an equation for my output gap. I'm just going to call that X here. I have an equation for my inflation here, pi, and I have an inflation here for my interest rate, which we often call the Taylor rule. And that makes up a static macroeconomic model. I also have a demand shock, which directly affects the output gap. I have a supply shock, which directly affects inflation, and an interest rate or monetary policy shock that directly affects the interest rates. What I'm interested in here then, for example, might be to trace out the effect of a demand shock. So I might identify a demand shock and can then see what happens to interest rates. But I still don't understand the mechanism. So more specifically than to understand the mechanism, I might be interested in how much of this effect of the demand shock on interest rates actually goes through inflation. And a very first approach that a researcher might use to understand this is to say, okay, I have my demand shock here. It would directly affect my output gap. That output gap itself affects the inflation rate, and inflation rate through this Taylor rule affects the interest rate. One kind of pitfall that a researcher would fall into then, though, is that at the same time, this interest rate actually also affects the output gap, meaning we have this general equilibrium kind of setting. And that's a problem. And we can visualize this problem much better if we actually transform this algebraic problem into a graphical problem. So what I'm going to do is I'm going to introduce nodes, and I'm going to introduce a node for my output gap, my inflation, my interest rates. And I'm going to denote them with like a circle, and I'm going to have a node for my demand shock, my supply shock, and my interest rate shock. And I'm going to denote them with squares just to distinguish what is an endogenous variable and what is a structure shock. And then I'm going to have an edge from like the shocks to endogenous variables or from endogenous to endogenous variables whenever a variable appears on the right-hand side of another variable, essentially. And what I can see here again, if I want to move from a demand shock to interest rates, I could move to the output gap directly to interest rates, to the output gap inflation and interest rates, and call that my effect through inflation, so the latter of them. But then I again still have the problem that actually interest rates can feed back into the output gap, and again go through inflation, etc., etc. So I have this infinite kind of loop, which means in this kind of graph, I actually cannot analyze the effect through inflation rates onto interest rates. So instead, what I'm going to do and what I'm going to claim for a second is that there's, for all these cyclic graphs, there's an equivalent kind of directed acyclic representation. And with equivalent here, I actually mean that it's causally and observationally equivalent. The only difference being there, instead of having the cycle, I now have direct edges from the demand shock to more than one endogenous variable. I can prove this actually in general, and by saying that if I have an n variable S-Varma model, they're going to be n factorial type of duct representations. Each of them represents an equivalent kind of causal and observationally setting. In these kind of duck representations, I then have two kind of relationships, so two type of edges. They have causal edges, which go out of structural shocks, and these are interpreted as direct causal effects. So, for example, from my demand shock on inflation, I have a direct causal effect of the demand shock on inflation, keeping the output gap constant. And then I also have carrying kind of relationships. So as a carrying effect, for example, we call the edge from pi to I, because all I'm interested there is what is the effect on interest rates if inflation was to increase 1 unit, keeping the output gap constant. And because nowhere there I actually brought in structure information from a structure shock, it's not a causal edge, but it's a carrying edge. And it turns out combining these causal edges with carrying edges, we can trace out various effects, and we can actually formally define what the transmission channel and the transmission effect is. One problem I have here, though, is that I have these n factorial kind of graphs. So technically, I have a lot of graphs to analyze. It turns out, well, that we can fix the representation in many research questions. And just mathematically, we would do this through what we call a transmission matrix, which is technically just the permutation matrix defining in which order the variables appear and basically the directed acyclic graph. And for the rest of this presentation, I'm mostly going to fix it to the representation that you can see here on the right. Once I have this representation, or once I have a duck, I can then define my transmission channel as simply the sub-collection of paths connecting a shock to an outcome variable. And I'm going to define the transmission effect as simply the effect flowing through the sub-collection of variables. It then turns out that I can also actually figure out what the total effect would be represented as in this graph. So the effect that we usually analyze using an impulse response function. And that's nothing else than the effect through all these paths. And intuitively, that makes sense, because if I would include any of these paths, so if I, for example, would exclude the edge of the demand shock and interest rates, then there would be an open kind of flow through which I could still send an effect and still change the interest rates. So the total effect must follow all paths. And because the transmission channels are a sub-collection of paths, there might be the possibility to decompose this total effect. And this decomposition actually always works out when my collections are non-overlapping, they don't share paths, and they're collectively exhausted. So to give an example, we can actually trace out the total effect of the demand shock and interest rates, which makes up these 4 paths here. So the effect is just added along these ones. And then I can look at the effect through inflation, which is just the first 2 terms, and the effect not through inflation, which turns out to be the last 2 terms. Because the two sets of paths are non-overlapping, but they are collectively exhaustive, they actually perfectly decompose the total effect. And that's going to be the case whenever, even if I have a large dynamic system. So the only problem that we're really left with is how we actually can effectively calculate these transmission effects using as little identification restrictions as we can. And here, to demonstrate that, I'm again going to focus on the effect for inflation. So I have a demand shock, and I somehow want to go to the interest rates, but I want to go through inflation, which technically makes up these 2 paths. And what you can see here is that the last edge, so the one from pi to I, is in common. So I can ignore it first and really focus on what's in parentheses here. What's in parentheses is basically the path of the demand shock to the output gap to inflation and the demand shock to inflation. But if we look carefully at it, that's actually all paths from the shock to inflation. And because it's all paths, it's going to be a total effect. More precisely, actually, it's a structural impulse response function of the demand shock on inflation. Once I am at inflation and now how much inflation changes, I only need to figure out how much then the interest rate will still change. And I can do this by following a thought experiment by which I ask how much a 1 unit increase in inflation, keeping the output gap constant, changes the interest rates. And that's exactly the carrying effect that I was mentioning earlier. And it turns out that's actually reduced form. That's a reduced form impulse response function or non-structural impulse response function, because I don't care which combination of structure shocks is used. I just need a combination of structure shocks that achieves an increase in pi without changing x, basically. And once I have that, I can combine my carrying effect with my structure impulse response function. So I simply multiply them in this case, and I get the effect through inflation. I can generalize this by essentially arguing that every path must start as the demand shock, must go to some endogenous variable, and then go from endogenous to endogenous variable, which means the first path from the demand shock to some endogenous variable that requires structure information. I can use a structure impulse response function for this. And then from endogenous to endogenous variable, that actually doesn't require any more structure information because no shock is involved. So I can get this from reduced form impulse response functions. which in general therefore means that each transmission effect, no matter how complicated it is, can always be computed using structural impulse-response functions and non and reduced form impulse-response functions. And in the paper, we give some more details. So we give essentially, once you have a transmission channel, how can you compute these kind of transmission effects? What it also means is that throughout here, we always start at the demand shock. So we are never actually interested in the supplier interest rate shock. And that's a general result. We never actually need to identify more than one shock. So the nice result here then implies that whenever you already have a shock identified, whenever you already do essentially impulse response analysis, you can now actually further decompose these impulse responses and analyze just how this total effect comes to be and what the mechanism behind it actually is. One problem that I'm facing still here though, right, is that problem that I have multiple or n factorial kind of representations. So I need to fix one or two of these representations. Mathematically, again, we only do this through the transmission matrix, permutation matrix, so it really just defines the ordering of the variables. Now, the reason why I have so many representations is because we're in a general equilibrium where everything kind of causes everything. We have a cyclical behavior. And if we want to break a cycle, there are many ways to break a cycle that essentially results in equivalent representations. And each of these equivalent representations or each of these transmission matrices defines essentially equilibrium in various different ways and therefore allows for different analysis. What it also does is to immediately signal whether two transmission channels are inconsistent with each other. So whenever I can analyze a transmission channel only in one representation, but not in the other, then that transmission channel is inconsistent with one of these representations of general equilibrium. In our case, that means that technically I have 6 representations, but because my research question is to affect through inflation on interest rates, I can ignore already 4 of them, and I'm actually stuck only with the first one and the third one. If I had a more precise research question, I might be even able to further filter them down. In the current research question, I cannot further filter them down. And what I should really be doing is actually analyze both this representation, which I didn't before, and analyze the effect in this third representation, and then compare whether there are meaningful differences or not. Once I have the static case, introducing dynamics is no problem because all we basically do is we take a dynamic model, we fix the maximum horizon at which we're interested in, and then we can rephrase the dynamic model into a static model. So all the intuition that I just explained with this 3-variable model actually carries over into n-variable models and dynamics, however complicated you want them, just that these graphs start to look more and more complicated because more and more edges are basically introduced. To demonstrate what we can basically do with transmission channel analysis, we have one application where we apply to monetary DSGEs. So here, that's a very standard Smeets-Bautis model, and we essentially take a contractionary monetary policy shock to a positive shock to the interest rates. And what we're again interested in is what the role of wages here basically is. So if we looked at the total impulse response functions, which are basically display here, is we see that there's an increase in interest rates. We see that that will lead through this hump-shaped typical downward response in inflation, but we also see that there's a downward response in wages, as at least for the first few periods. So we might think that these wages, the downward pressure on the wages, actually will also induce a downward pressure on inflation. And qualitatively, we can argue about this by actually looking at the equations. Because if we go back to the model, we can actually see the standard econ behavior that higher interest rates kind of discourage consumption investment. So demand reduces, which puts downward pressure on prices. But this downward pressure on demand also lowers labor hours, which lowers wages, which then lowers kind of prices. Problem with this here is that I can qualitatively argue how important wages are. So this in the second, so from the second to third point, basically, but I can't assign a quantitative value to it. And we want to assign the quantitative value to it. So I'm going to use transmission channel analysis to assign this quantitative value to it. To fix the representations, we chose 2 representations that are consistent with basic macro here. The first one I'm going to call the second round effects, where I have essentially in R my real interest rates, my Y just summarizes a subsystem of output variables in my labor hours, my W is my wages, and my pi is my inflation. And in the second round effects, essentially what I'm allowing for is that my demand contemporaneously feeds into wages, and then that basically can explain inflation, which is the behavior that we would usually derive from the model qualitatively. However, for macro, we also know that wages can react to already priced expectations. So we might also have that wages directly react to monetary policy, and that can itself feed into demand then, and then into inflation. So we take exactly the opposite side around. What I'm going to do is I'm going to compare the two decompositions. I'm going to see if they meaningfully differ or if we can have a consistent conclusion about how important wages actually are, no matter the decomposition. And we can visualize these decompositions in a very similar plot to how we would usually plot impulse response functions. So along the x-axis, I have my horizon of the impulse response, along the y, just the effect size. And on this black scatter line, you have the total impulse response function that I would usually look at here of the monetary policy shock on inflation, basically. In my bars, then I have the decomposition. So the red bars are always my wage channel. That's the effect through wages, which we're really interested in. In my blue, I have the demand channel, so everything that doesn't involve wages, basically. And then in the red and the more solid colors, I have the second round effect. So what I had on the left side here, and then what I had on the right side are going to be the more faded bars here. And what can clearly see now quantitatively is that the initial response in inflation is completely driven by the demand channel, with wages actually having a somewhat upward pressure on inflation there. However, from one period after the shock onwards, we see that wages become more and more important. And from like 3 periods after the shock, wages make up more than half of the reaction of inflation to the contractionary monetary policy shock. What we can also see here is that actually the two decompositions that we produce are very, very close to each other. And that can be followed back to basically the idea that it doesn't matter that the feedback of wages into the demand system doesn't matter, but the feedback of demand into wages is really what matters here. And that's why they're so similar. So to leave some time for potential questions, I'm going to just go to the conclusion. So we have this new methodology, or we propose a new methodology that we're going to call transmission channel analysis, that essentially allows to decompose total impulse response functions into the mechanisms or transmission channels that make up these kind of effects. We derive this actually using potential outcomes and like formally causal graphs, so at least they're causally coherent. And really the nice thing is that we only require this one identified shock. So whenever someone is using structure impulse response functions already, they can decompose it. We have a paper, we have a package, there's a new version also coming for the package. So if you want to apply it, for example, to DSGs, the NEA versions are coming soon. Thank you very much.